from hydrocarbons. Under that, the first method is by ozonolysis of alkenes, which you have already studied in grade 11 under hydrocarbon chapter. It is a quick revision of what you studied in grade 11. Here, I start from alkene. The general structure of alkene is represented like this. You have C double bond C. And I am going to make use of ozone here, O3. Beginning, you will get ozonide. What is ozonide? Across C double bond C, 2 oxygen atoms get added. So, I can represent it this way. So, one bond disappears and 2 oxygens are added across the double bond. Now, I am left with one more bond. So, in that bond, one more oxygen atom gets inserted. So, 2 oxygens are added across C double bond C. Then one more oxygen is inserted in between the single bond between the 2 carbon atoms. The product formed here is called ozonide. Now, this ozonide is subjected to hydrolysis in presence of zinc. So, what way this compound undergoes cleavage? Point number 1, the bond cleavage takes place over here, it takes place here, and also it takes place here. So, because of that, what are the compounds we are going to get? We are going to get, it is a C double bond O. From this side, we will get C double bond O. So, from the other side, again, we will get C double bond O. In addition to that, what we get is hydrogen peroxide, H2O2. So, here you have H2O, will take away this oxygen, gives you hydrogen peroxide. Now, the question is, why should I make use of zinc? If you do not make use of zinc, imagine one of the products formed here is aldehyde. And along with that, hydrogen peroxide, which is an oxidizing agent, is formed. What happens? Hydrogen peroxide oxidizes formed aldehyde into carboxylic acid. So, if you want to stop the reaction at aldehydic stage or ketonic stage, I have to ensure that hydrogen peroxide does not oxidize, and that can be done by providing a reducing agent like zinc. Or in other words, zinc prevents the oxidation of aldehyde to carboxylic acid by hydrogen peroxide. And as far as various products are concerned, it depends upon the groups that are attached to C double bond C. If suppose you have double bond CH2 part in alkene, when you subject it to ozonolysis, you have to get CHO group. So, very clear, this is a commonly asked question in the competitive examination. If the product of ozonolysis of an alkene gives you let us say a formaldehyde, it is a HCHO, formaldehyde, the starting alkene should contain methylene group, double bond CH2. On the other hand, if it contains a CHR group, or in other words, this doubly bonded carbon atom has undergone one substitution, then the product of ozonolysis will be RCHO. You get any other aldehyde. And the last possibility is this doubly bonded carbon atom will not have any hydrogen. So, we have CRR dash. Under such cases, when you bring about ozonolysis, what we get is RC double bond O R dash. Or in other words, we will get ketone. So, this is what is very, very important. So, formaldehyde is formed, the starting alkene must contain double bond CH2 group. If you get any other aldehyde, the starting alkene must contain double bond CHR group. If the starting alkene contains double bond CRR dash group, the product of ozonolysis must be ketone. So, our second method under this is by hydration of alkynes. You might have studied this reaction last year under grade 11 as a method of preparation of, under chemical properties of alkynes. If suppose I start from ethyne, the product obtained is always aldehyde. On the other hand, if you make use of alkyne except ethyne, the product obtained is always ketone. You know about the reagents that are used to bring about this reaction. We have to make use of 20% H2SO4. Mercuric sulfate must be used as a catalyst, and reaction has to be carried out at 343 Kelvin. Let me first explain the reaction by considering hydration of ethyne. So ethyne, I'll write like this. I told you it is a 20% sulfuric acid. It is mercuric sulfate catalyst, 343 Kelvin. It is a hydration reaction. We have to add a water molecule across C triple bond C. So during addition reaction, triple bond becomes a double bond. The intermediate formed is CH2 double bond CHOH. This is actually enol. You have a double bond and a OH group. It has to be enol. Now this enol undergoes tautomerism. I can show tautomerism like this. In other words, hydrogen goes out in the form of H plus that will combine with C minus here. As a result, this group becomes CH3, double bond becomes single bond here, and here single bond becomes double bond. Or in other words, this reaction is actually a tautomerization reaction. So the product obtained here is a CH3, and here you have a single bond, and thereafter you have C double bond O, single bond H. So what is the compound that is obtained here? It is nothing but acetaldehyde. We get acetaldehyde. I'll go to hydration reaction under the same conditions. So water molecule must be added according to Markovnikov's addition rule. So product obtained is CH3, it is COH, a double bond. Here you will have a CH2, and now this undergoes a tautomerism in the same way as I told you. The product obtained in this case should be acetone, in the same way, if I consider one more example, diphenylethyne. Reaction takes place in the same way. That gives you a C6H5COH, a double bond CH, then you will have C6H5. So reaction proceeds through tautomerism. So we get C6H5 C double bond O. Here this becomes CH2 and then we will get C6H5. So this will be the product form. Again, what is obtained is ketone. So this is actually a benzyl phenyl ketone. Benzyl phenyl ketone. Yes. In today's class, we shall start from general methods of preparation of aldehydes and ketones. Under that, the first one is starting from alcohols. Under that, we'll first start by oxidation reaction. This reaction you have already studied under previous chapter, alcohols, phenols and ethers. That's why it is just the repetition of whatever you have studied in previous chapter. Here I'll start from a primary alcohol, RCH2OH. Primary alcohol. I'm going to subject it to oxidation. When I subject it to oxidation, remember it loses a molecule of water. And what is the product we get? We are going to get RCHO, and you already know that this is aldehyde containing same number of carbon atoms, and this aldehyde undergoes further oxidation. When it undergoes further oxidation, it will give you a carboxylic acid. It is a RCOOH, right? It is a carboxylic acid containing same number of carbon atoms. On the other hand, you know that if suppose I start from secondary alcohol, which I represent it as RCHOH R dash. So I'm starting from secondary alcohol. I'll subject this to oxidation. A molecule of water is removed. The product obtained would be, ketone RC double bond O R dash. I'm going to get ketone. Of course, this ketone contains same number of carbon atoms as in starting secondary alcohol. Now, the question is, what can be the various oxidizing agents that I can make use of? The various oxidizing agents that can be used are, I can go for acidified potassium permanganate. So, I can use KMnO4 in acidic medium, or I can go with acidified potassium dichromate K2Cr2O7, acidified potassium dichromate, or I can also make use of CrO3 in aqueous medium. But the problem of using these oxidizing agents is that the first reaction, that is oxidation of primary alcohol, does not stop at aldehyde. It directly gets converted into carboxylic acid. So, if we want to stop the oxidation at aldehydic stage, we have to go for one of the two methods. What are those methods? You have already studied under previous chapter. We can go for using PCC, pyridinium chlorochromate, in presence of dichloromethane solvent, or I can go for CrO3 in non-aqueous medium. So these two reagents will stop the oxidation of primary alcohol at aldehydic stage. And these two reactions you have already studied in previous chapter. Second method under obtaining aldehydes and ketones from alcohols is by dehydrogenation. Already you have studied about dehydrogenation. The process is carried out in the vapor phase, or in other words, I have to consider vapors of primary or secondary alcohol. What about the catalyst that can be used? It's very, very important. Either we can go for copper catalyst at 573 Kelvin, or I can go for silver catalyst at 523 to 573 Kelvin. What way I can represent the equation for the reaction? Again, I'll start from vapors of primary alcohol, and these vapors of primary alcohol should be passed over heated copper catalyst at 573 Kelvin. This molecule loses a molecule of hydrogen, so H2 is removed. What else we get? We are going to get RCHO. So RCHO is nothing but aldehyde. Same way, if I start from the vapors of secondary alcohol, and pass the vapors over copper catalyst at 573 Kelvin, again dehydrogenation takes place, H2, and the product obtained is a ketone RC double bond O R dash. The advantage in the first case is that because the byproduct formed is hydrogen, which is a reducing agent, it will prevent the further oxidation of aldehyde into carboxylic acid. That's why it is possible to stop the oxidation at aldehydic stage. Second method is starting from hydrocarbons. Under this, we are going to start from the first one by ozonolysis of alkenes. So to understand this, I am going to start from alkene. You have C double bond C. You have two bonds like this. Alkene. I am going to make use of ozone. How can I consider the formation of the product now? In ozone, to make the concept simple, I'll consider that it is an addition reaction of O double bond O across C double bond C. Now whenever you consider addition reaction, you know that double bond should become single bond. So here whatever C double bond C is there, it becomes C single bond C. Same way here O double bond O becomes O single bond O, and these two oxygens are added across the two carbon atoms connected by means of double bond. As a result, the product obtained would be carbon has two unsatisfied bond. Here you have carbon, you have two unsatisfied bonds, and during addition reaction I said double bond becomes single bond. I don't indicate it now, and these two oxygens are added across C double bond C. So the two oxygen atoms are added. What is the next point? The next point is, I'm left with one single bond between the two carbon atoms. In that single bond, remaining oxygen atom of ozone gets inserted. That's why I'll get C single bond O and again single bond. So I repeat, I can consider this reaction as addition reaction across C double bond C. Initially we are adding a molecule of oxygen. During addition reactions, we know double bond becomes single bond, and here again double bond becomes single bond, and this O2 gets added across the C double bond C. So whatever one bond is present between the two carbon atoms, one oxygen atom gets inserted. So this is the product formed, and this product is an unstable product. It is called ozonide. Now this ozonide undergoes decomposition in presence of zinc and water. You have Zn and water. This undergoes decomposition. So what way I can show the decomposition? This particular bond gets cleaved, and here this bond gets cleaved, and here again this bond gets cleaved. So these bonds are broken. Whenever these bonds are broken, what do we get? Here I have C with the two unsatisfied bonds, and here you have oxygen. It is a C double bond O plus. You consider this side, you have C, right? You have two bonds, and then you have a double bond O. And of course, you can make out whatever oxygen is present will combine with water. So it gives you a molecule of hydrogen peroxide. Now, the problem with this hydrogen peroxide is, it is an oxidizing agent, and this oxidizing agent oxidizes if at all one of the products happens to be aldehydes. Those aldehydes will be oxidized to carboxylic acid. So if I don't want to get a carboxylic acid, I have to prevent the aldehyde from undergoing oxidation in the presence of hydrogen peroxide. So how do I prevent the oxidation? I have to provide a reducing agent. So which is the reducing agent? You are making use of zinc. So what is the role of zinc here? During ozonolysis, the byproduct formed is hydrogen peroxide. Hydrogen peroxide, being an oxidizing agent, will oxidize any aldehyde if formed to carboxylic acid. So if I don't want aldehyde to undergo oxidation to carboxylic acid, I have to control the oxidation, and that is done using the reducing agent like zinc. Now, this particular reaction, whatever I have highlighted, is very, very important for various examinations, like competitive examinations. So what all those points you are supposed to know for various competitive examination? Now, let us just analyze the different groups that can be present on doubly bonded carbon atoms. For example, let us say you have a double bond here as it is, and you have a carbon atom, and on this carbon atom, let us say both the bonds are satisfied by hydrogen CH2. So what should be the final product I am going to get? So look at this particular product. What is the requirement? Here these two bonds are satisfied by hydrogen. That means here these two bonds must also be satisfied by hydrogen. So if you have two hydrogens over here, what is the product? The product is HCHO. It is a HCHO. So what is that HCHO? HCHO is nothing but formaldehyde. In other words, it's very clear that in the starting alkene, if suppose we have double bond CH2 group, the product of ozonolysis will be formaldehyde. The same concept is asked in a reverse way. One of the products of ozonolysis of an alkene is formaldehyde. Which particular group does it indicate in the starting alkene? Answer is simple. In the alkene, you have double bond CH2. Hope it is clear. On the other hand, imagine here one bond is satisfied by R and another bond is satisfied by hydrogen. Or in other words, the other possibility is this carbon, one hydrogen and one R. You have double bond CHR. What about the product formed in that case? So go to this, one bond should be satisfied by R, the other bond should be satisfied by hydrogen. Or in other words, what will be the product of ozonolysis? I will have RCHO. Or in other words, if you get any aldehyde other than formaldehyde, it clearly indicates the presence of double bond CHR type of group in the alkene. What is the last possibility? These two bonds, if at all, are satisfied by two different groups, which I am going to represent it as R and R dash. Imagine here I will have R, here I will have R dash. So what is the product you will get? Here you will have R, here you will have R dash. So the compound what you are going to get will be ketone, because the compound will be RC double bond O R dash is nothing but ketone. So during ozonolysis, if the alkene contains the group of the type double bond CRR dash, then the product of ozonolysis will be RC double bond O R dash. And these points are very, very important for your competitive examination. Now, in order to explain this, let me consider one simple example. I am going to start from this alkene. You know how the reaction takes place during ozonolysis. So the formation of ozonide, I'll represent it like this. You have a C and here you have CH3. Here single bond O, here it is carbon, and here you have hydrogen and here you have hydrogen, and here two oxygens are added across the two carbon atoms. And then in the presence of zinc and water, ozonide has to undergo decomposition. So when it undergoes decomposition, it is like this. You can clearly guess as to what are the products you are going to get. Here you can make out the formation of CH3C double bond OCH3. So one product is acetone CH3COCH3, that is acetone. What about this particular product? Here you can make out it is a HC double bond OH. So I'll get HC double bond OH. So these are the products of ozonolysis. And also remember, for your competitive examination point of view, if you are given the products of ozonolysis, how do you arrive at the structure of the starting alkene? In order to understand that, I am going to consider one specific example.